Okay, now we'll do a sample problem for the welded connection. And for the sample number problem 1, we have here determine the design capacity of the welded connection shown. So we have this a gusset plate which is 16 mm thick, and the material is specified as A572, meaning that we'll have a different Fy and Fu value for this A52 compared to A36. Our bar is L 200 by 200 by 12 mm, and we have A36 steel. Okay, so again we have the different values for your Fy and Fu of these two steels. Our welded joint is 8. This is the the fillet size. Yeah, this one's the length. So it says here we have 8 mm fillet size, and the length is 380. So meaning 380 here, and this is also 380. There's another volt symbol here that I've provided. Okay, so if you recall our procedure for analysis, we just actually first obtain the equations, and then um, we check the capacity of the weld metal, this weld joint itself, or this weld metal itself, and then we will have to check the shear yielding and shear fracture of the base metal. So since we have two materials here, then we have to check um, the failure of this base metal, of this bar, of this angle bar or equal leg angle, and then we also have to check another failure yielding and rupture and shear for this gusset plate. Okay, so I have already provided here the information that we need, although um, you can also obtain this from the tables that we had, um, especially for this steel. I think we have that in the lecture handouts of Introduction to Steel Structures. So we have Fy, the yield strength, and the ultimate strength. Now for this, we can obtain this from the table. So since we have E70, and our Fy is 415 and Fe is 485. Okay, so let's solve first. Solving for the capacity of the weld metal. Okay, our equation, you can solve that per unit length, or we can directly solve the factory capacity Rn, which is just equal to the reduction factor times 0.6 FE That's the Fy. That's this Fy 415 times the throat length and the area. We have 0.707 times the size. This size is just 8 mm times the weld length. Okay, what's the weld length? The weld length is just simply 380 times 2. Okay, so if we substitute the values, we get 0.75 times 0.6 times 415 megapascals times 0.707 times 8 mm times 380 mm times 2. Now, if we solve this, we have 802.76 kilonewton. Right, now the next step is to solve for the capacity of since we have two base metal here, then, and we have different steels. Therefore, we'll have to check the each steel. Okay, so for now, let's solve the capacity of L 200 by 200 by 12. Okay, so we can write it this way. Since we have two conditions for the base metal failure, then we can just write minimum of the two condition, which is the failure in shear yielding and another one, failure in shear rupture. Here we have a reduction factor, which is this one times the um, shear strength, 0.6 Fy, times the thickness times the weld length. And this condition, another condition here, reduction factor times 0.6 Fu, d times the weld length. Okay, but this one, the reduction factor is 1.0. Here is 0.75. Okay, so now let's substitute the value. We have 1.0 times 0.6 Fy. So take note, this is L 200 by 200 by 12, meaning that the steel is A36. So 0.6 times A36, what is the Fy? That's 250. So times 250 times the thickness and the weld length. Now for the thickness, we have a thickness of 12. So let's just write 12 times the weld length. Now the weld length is 380 times 2. So we have 760. And for the shear rupture, we have 0.75 times 0.6 of the ultimate tensile strength, 400, times the same thickness, so 12 times 760. Okay, so we calculate this. This is 0.6 times 250 times 12 times 760, and divided by 1000, we have 1368 kilonewton. And for the shear rupture, we have 0.75, 0.6 times 400 times 12 times 760. We have 1641.6 kilonewton. So therefore, this one, the capacity of the L200 by 200 by 12, that's gonna be 1368 kilonewtons. Okay, so the next step is to solve for the base metal capacity of the gusset plate. Okay, so let's write it here. 3, solving for the base metal capacity of the gusset plate. Okay, so again, just apply the equation. That's the minimum of this 0.6 Fy times d. This one is the same, 0.6 Fu times d. Okay, and take note, since this is a gusset plate and we are given this type of steel, A572, then meaning that the Fy that we'll use is 345 and the tensile strength is 450. Okay, so now let's substitute all the values. What we get here is 1.0 times 0.6 times Fy 345 times 345 times this thickness, but the thickness is we have 16 right? So 16 thick. That's gonna be 16 times 760. And here we have 0 0.75, 0 0.6 times 450, okay, times 16 times 760. Okay, so if we do the calculation, 0.6 times 345 times 16 times 760 divided by 1000, then we get 2517 kilonewton. And the other one, 0.6 times 450 times 16 times 760, so we get 2462.4 kilonewton. So therefore the design capacity of the welded connection is phi Rn is equal to the minimum of the three, which is the first one is 800. So the capacity of the weld metal, it's 802.76 kilonewton, and the other one is 1368 kilonewton. And this one, the minimum is 2462.4 kilonewton. 2462.4 kilonewton. So therefore we have a this one, 802.76 kilonewtons. Okay, so that's our design capacity. Now let's check. Okay, this is our design capacity, and now let's check the checking code requirements. Okay, so for the code requirements, we have we'll check first our A mean. So A mean is equal to in our lecture handouts, that's table 14-3. Since our I mean not our A, but the thickness, our thickness, let's say thickness of the material is or R, let's say we have 12 and 16 and we'll take the minimum thickness, that's the 12, or the minimum between the two. Since our thickness is, let's say, 12 then our minimum A mean is equal to 5 Okay, so that's from table 14-3. And for the A max, so for our maximum weld size, since our thickness is 12 okay, so I'm referring to the governing thickness, then therefore our T max is 12. Okay, wait, we'll add another condition. Since our T is 12 therefore, or let's say which is greater than or equal to 6 okay, so our condition is our thickness is 12 mm, which is greater than or equal to 6 mm. Therefore, A max is T minus 2 mm. So therefore, this is 12 minus 2, so we have 10 mm. Okay, that's our A max. This is our our A minimum weld size. Minimum weld size is our maximum weld size. Therefore, our if we check that, our A is 8 mm, right? That's in our problem. So A is equal to 8, 8 mm. So our A is greater than our minimum, which is 8 mm, and it is less than our maximum. Therefore, code requirement is met. Code requirement is met. And for the effective weld length, you can check the effective weld length is equal to 4A. So 4 times A, that's just 8 times 4, which is 32. And our weld length is way beyond 32 mm. Therefore, code requirement is met. Okay, so let's have a review on what we did in our problem. So the computation for the analysis time of problem for this welded connection is just straightforward. So first we solve for the capacity of the weld metal, because our limit state is that this welded connection or welded joint can fail in the weld metal or in this base metal. So first we solve for the capacity of the weld metal. We apply the equation. We consulted the tables, appropriate tables for that. If, of course, in case that this data is not given, then you have to find it. Okay, and we get a value of 802.76 kilonewton. Now, we check the capacity of the base metal, but since we have two base metals here, then we have to check each of them. So first, we check the this bar, the capacity of the bar, and we calculated the capacity for shear yielding and then the shear rupture. And we just substitute the equations and we get this value. Okay, and then the next step that we did is we solve for the base metal capacity of the gusset plate, and we just apply the equations, and then we obtain that. Then after that, we calculated the design capacity, which is simply the minimum of the three conditions or the three limit states that the values that's produced from the three limit states, and we say that our factory capacity is 802.76. Now, for the last part, we check the code requirements on the minimum weld size and then the maximum weld size. Okay, so for the minimum weld size, you just go to the table, and since we have a thickness of 12 for the angle bar and then 16 mm for the gusset plate, then we just choose the minimum. We compare that, or we find that in the table. So in this range, or just a range, I think that's 6 to 13, 6 mm to 13, or over 6 mm to 13. Then it says that the minimum weld size is 5 mm. For the maximum, if the thickness is greater than 6 mm, then our equation would be thickness minus 2. If it's not, if it's less than 6 mm, then it's just the thickness itself. Okay, so we just substitute the equation, we get this, and yes, we say that the code requirement is met because we are in the range of minimum maximum. And we also check the weld length, and we are way longer than this minimum weld length. Okay, so now we will do another problem for this welded connection, but this time we will have slightly different, I mean, different weld configurations. So we will now include a longitudinal weld and a transverse weld. Okay, so the problem says we have a 150 by 18 mm, that's plate. So this is our plate, so meaning that the cross section is just something like this, and it's welded to a gusset plate 22 mm. And it says that we're using 10 mm fillet weld. The steel is A36 and the electrode used was E70, electrode 70, and we were asked to determine the design capacity of the section. Okay, so we have actually a base metal of I think this is A36, so meaning this one is A36, and this gasol plate is also A36, so meaning that we don't need to check the base metal capacity of each, because we can just take the minimum thickness, and that's gonna be it. Okay, so for now, since we're not information or data, then we have to obtain informations necessary. Okay, so first we have A36. So for the A36 we have I think the Fy is equal to 250 megapascals, and Fu is that's 400 megapascals. For the E70 we have I think that's just the same with our first problem. That's 415 and 485. So this is Fy is equal to 415, 485 megapascals. Okay, our weld size, our A, so that's 10. So they're all 10. So that's 10 mm, and our weld length. So our weld length, we have a weld length, a longitudinal. So let's say this is L, which is just 200 plus 100. So we have 300. But for the transverse, we have 150. Okay, so I guess we'll also write the thickness here. So thickness, since they're just the same, A36, we'll just choose the smaller thickness. So this one is 18, and the gusset plate is 22. So let's just say this is 18 mm. Okay, so next, solving for the weld metal capacity. Okay, so how do we solve this? Let's first solve our nominal strength per unit length, and that's I think the 0.6 FEXX times the 0.707 times A, times the weld size. So 0.6 times our FEXX, so that's 415 megapascals, times 0.707 times the weld length of 10, weld size, And we can now solve this. 0.6 times 415 times 0.707 times 10, and that's 1760.43. Take note, this is Newton per since this is mm per mm. Okay, so now let's solve for the factored capacity. For the factored capacity, it says that if we have a combination of a longitudinal and a transverse weld, then we should check I think that's the maximum value of the two. Yes, that's the maximum. So that's theta, the reduction factor, times the max of either this one plus r. Of course, this is the capacity of the longitudinal weld, and this one is the capacity of the transverse weld, or 0.85 times this plus 1.5 times the that's the transverse weld times 1.5 plus longitudinal weld times 0.85. Okay, so now let's substitute the value. The reduction factor is 0.75 as always, times the maximum of this one. So if you recall that I discussed this in the lecture, in the first part of the lectures here about welded connections, that a transverse weld is actually a much higher or is much stronger, more stronger compared um, to this longitudinal weld. However, for simplicity's sake, we just take the or we just assume it the same. So meaning that we don't have to calculate here the increase for this transverse section. It's actually 1.5, and the equation is actually the actual equation that you'll find the code is this one: 0.6 FEXX times 1.0 plus 0.5 sine raised to 1.5 times theta. So that depends upon the okay, so this is the theta. So example, this is the weld length, so this will be the theta. So if you have a value of purely let's say a 0 degrees, so sine 0, this is just, if sine is 0, then you have this value of inside these parentheses, you have a value of 1. But if your theta is 90 degrees, what you get is, since sine of 1, that's just sine of 90 is just equal to 1, so 0.5, so that's going to be 1.5. So you have an increase of 1.5 in the capacity for the transverse, but again, for simplicity's sake, we just use the same. Okay, so meaning that we can take this value 1760.43, that's in Newton per mm, and we just add the length. So we can just add this length, this length, this length, and then this length. So which is just 300 plus 150. So this is the 300 plus 150, and that's going to be 450 mm. And here, this is the same 17, except that we have to 0.85 times the length, the longitudinal length, that's 300. Okay, plus 1.5 times 150. Okay, so 0.75 times the top condition, we have 1760.43 times 450. Okay, divided by 1000, we have times the max of 792.2 kilonewton, and this condition is 1760. Or we'll just solve this. 0.85 times 300 plus 1.5 times 150 times 1760.43. Okay, divided by 1000, and that's 845 kilonewtons. Okay, so therefore you can write it as 0.75 times 845 kilonewtons. 0.75 times 845, that's 633.025 kilonewtons. Okay, so I guess I don't have much time now. We'll continue our this sample problem in the next video.